Okay, hello. I can see people are starting to come on in. So welcome to the Meet the Experts session for gravitational waves as part of Cardiff Science Festival. We'll start the session properly in a couple of minutes. My name is, let me go on to the another slide in a second. So my name is Chris North, and I'll be hosting, and you should also probably be able to see on screen Grace. Before we do full introductions, let's start off with just a poll. We'd like to see who is here. So while we're just doing the initial introductions and so on, I'm waiting for everyone to come on in. We'd like you to go to menti.com and use the code that's there, 219914, and it will ask you a few questions. You can alternatively, if you have such a device, is scan the QR code on the screen, or you can click the link in the chat that Grace is about to send to everyone in the call. So I'll let everyone do that. So I'll leave that on screen just for a second. So this is a Zoom webinar. So I'll put up a housekeeping slide in a second, just so everyone knows what is going on. I'll just give people a chance to click that link and type in the code. Okay, so that should be 219914. I said it's in a chat there. Okay, so the housekeeping for this session. This is a webinar, not a normal Zoom call, for those who have been in normal Zoom calls before. So you will find that your video and audio are disabled because this is a webinar. You should find at the bottom, there's a Q&A option where you can type in a question, and you can ask a question anonymously if you prefer, or you can add your name and we'll be able to say who is reading the questions. You should also be able to raise your hand and chat. So if you type things into the chat, then people will be able to see them. We can ask questions that appear there. But for ease, while we're running through the questions, it would be great if you can put them into the Q&A option that appears. And I can see we've already got questions starting to come on in. Okay, so introductions to who is here. So on the screen at the moment, you can see a slide with some faces on, and hopefully you can also see the faces on the videos as well. So there's myself, I'm Chris North. I'm the Director of Recruitment and Admissions and the Head of Public Engagement here in the School of Physics and Astronomy at Cardiff University. And I work with a number of the colleagues that we're going to see later on in the call. And I'm joined by Grace. Grace, do you want to say something about yourself?
Yeah, hi everyone, my name's Grace. As it says on the screen, I'm the Ogden Outreach Officer at the School of Physics and Astronomy at Cardiff University. It's really great that you're all here with us today, so thanks for coming along.
And we'll soon meet some panelists. So here is a slide with the panelists we're going to meet later as part of this, or very shortly, in fact. We'll meet them. So they'll be giving a short introduction, a little bit of a short few minutes about them and their work, and then we'll move on to questions from the audience as well. Before we do that, Grace, have we got much on the Menti? Is there stuff we should show?
Yeah, absolutely. We've got quite a lot of people filling it in. So is that okay if I share those slides?
Yeah,
let me
stop sharing, and you can share those slides, and we'll just see. It's just interesting to see who's here with us.
So I'll share my screen there. So hopefully you should be able to see on my screen who we've got with us. So the first question was, I am a. Great to see we've got a real range. So quite a lot of interested adults, but also a lot of secondary students. We've got one primary school student, one university student, and interestingly, one person who calls himself a scientist. When I set this question, I said that you could answer as many times as you wanted. So I hoped that some people would call themselves maybe a primary school student and a scientist. So I think, yeah, I like to think everyone can be a scientist, but it's great to see who we've got with us. So on my second slide, we've got where in the world are you joining us from today? So it's great to see loads of people with us from Wales, but also people from much further abroad as well. So we've got London and England, but we've also got France, we've got Bath, we've got Slovakia. That's really exciting. Thanks for coming to join us. And yeah, and India. Wow, cool. So welcome everyone.
Pittsburgh, USA as well. Excellent.
Oh, I didn't see that one, sorry.
Yeah, just at the bottom, yeah. Excellent. A nice range.
And then I asked how much people thought they knew already, so our speakers can pitch their talks. And it's nice to see we've got, people consider themselves pretty much in the middle. We've got a real range. Some people think they're experts already, and some people are still asking what are gravitational waves. We've got in the middle. And then a final couple of questions. Have you heard of gravitational waves before? Yeah, loads of you, really great to hear. I talk about gravitational waves with my friends and family. Few of you, hopefully after this talk, you'll all be talking to your friends and family about gravitational waves, we hope. I have read about gravitational waves in the media or online, more of you, so they're very topical in the last couple of years. And I consider myself to be a scientist or scientific, 6.2 out of 10, so 62% of you, great to hear. So I'll stop sharing with that and hand back to you, Chris.
Excellent. I will share my slides again. There we go. So I think great to see a little bit about who's joining us here. So wonderful to see everyone. I think we'll crack on with the first little introduction. And in fact, we're going to start with Professor Bernard Schutz. So Bernard, if we turn on your video, and we should see you appear on the screen. And the way this will work is I'll be doing the screen sharing just to try and keep everything seamless. So you will hear a little bit of a next slide, please, now and again, if I don't quite spot it. So that's the way this will go. So Bernard, do you want to? I'll go on to your first slide, and you tell us a little bit about yourself and your work.
Yeah, it's great to be here, Chris, and to see so many people who have an interest in gravitational waves and I want to talk about them with us. I'm the ancient person in this set. I did my PhD way back in 1971, and came to Cardiff a few years later as a lecturer. And in the mid 1980s, I started working on gravitational waves. I'm a theorist. I'm not an experimentalist, so I was interested in the waves themselves and how to detect them from the point of view how to dig them out of the data, and that's what I was working on. This field got more and more rich and interesting, and in 1995, I was invited to go to Germany to set up a new institute where gravitational waves was one of the topics. And then when I retired from that, I came back to Cardiff because I didn't want to give up doing those things. And I set up a data institute at Cardiff, but since around 2017, I've been doing mostly just gravitational waves again, which is really great. It's just a field that's full of action and very rewarding to have been in it for such a long time and see where we are right now. I thought I'd just answer a little bit about giving a picture of what gravitational waves are. Nothing goes faster than light. That was something that Einstein predicted such a long time ago before he even started worrying about gravity. But it has an implication which he understood right away, which is that if gravity changes here, so if two stars or a planet goes around the sun or whatever, they're always changing gravity. That change can't be registered somewhere else in the universe except after a delay, which is something like the speed of light. And so when he did his theory of gravity, general relativity, it turned out that the gravitational waves, that is that propagation through space of this gravitational changes, that was going at the speed of light. And so you just need to think of them as waves of gravity, and there's a lot of analogies with other kinds of waves. There's also something special about them, which is that they're gravity described by Einstein as the curvature of space and time. And so gravitational waves are actually vibrations of space. and they're analogous to sound waves, vibrations in air, but there's no air in outer space, and the gravitational waves propagate through space just because they're actually vibrating the space itself. Now, there are many analogies with the electromagnetic waves because they go at the speed of light. And one of them, if you know about electromagnetic waves, you know how they polarize, that there's two polarizations. Usually you could say a polarization that way and a polarization that way. And if you have two pieces of Polaroid or two lenses from a Polaroid glasses, and you have one of them like that, and then you turn the other one like that, you'll block all the light. So there's only two polarizations. The same is true about gravitational waves. There's only two polarizations, but they're not waves that are like forces that are going along a line. They're waves of tidal forces, and they stretch things in the same way that the Earth gets stretched by the moon, and that's what we call the tides. Gravitational waves carry this stretching action of gravity, and this illustration, this animation, shows that you get stretched in sort of this way, and then you get stretched that way, and so on. And there's two different polarizations there, but they are rotated not by 90 degrees, but only by 45 degrees. And that's all there is in the gravitational wave. If we had a gravitational wave polarimeter, we could, in principle, block all the gravitational waves, but that's not how gravity behaves. Gravity goes through everything, so you can't construct a polarimeter anyway. So that's a little bit of an introduction to gravitational waves. Chris, could we have the next slide? The gravitational waves are interesting to us, not just because Einstein predicted them, and it's great to verify that the prediction was right, but because they carry information. And what we're doing now with detecting them is a new kind of astronomy. And it's the astronomy of the dark side of the universe, because we're getting gravitational waves most of the time from two black holes spiraling together and merging. And those are events that we wouldn't be able to detect any other way. They don't typically give off any kind of electromagnetic waves, and so they don't appear in our normal astronomical telescopes at all. There are occasional times when we have a couple of stars, a couple of neutron stars that also spiral together and merge, and they explode, and then we have a spectacular thing for the telescopes as well as for the gravitational wave detectors. But the important thing is we want to know the information that gravitational waves contain, and the problem is this polarization. I mean, you should think of our detectors, they're not directional. They're not like a pointed telescope. They're much more like putting a microphone up to detect sound. These vibrations of space just run through space, and our detectors will vibrate a bit when the gravitational wave comes through, but we don't know where it's coming from with one detector, and we don't know what the polarization is with just one detector. So we have to build a network of detectors around the world, and this picture shows with the yellow spots the detectors that are operating and that have been built in different countries that cooperate with each other. We pool all the data, and we can triangulate directions because the waves arrive, let's say, in Japan before they arrive in Italy, and then before they arrive at one of the American detectors, and we can triangulate from that where the wave is coming from, and then we can decipher all the other information. So it's a big worldwide project, and it doesn't work unless everybody works together. And so you see those yellow detectors. There's also another detector there in sort of orange color, which is LIGO India. That's under construction. We're expecting that to come on in the middle of the 20s. So yeah, I hope that starts off the discussion.
Thank you very much, Bernard, for that overview. We'll move on to our next panelist to do an introduction. So let's move on. Dr. Keiko Kokeyama has recently joined us here in Cardiff. So Keiko, you should be able to unmute and put your video on. There we go. Yes, we see you. The floor is yours to explain a little bit about yourself and your work.
Yeah, thank you, Chris. Hi, everyone. Nice to virtually meet you. My name is Keiko. Yeah, so this shared page shows my research history. I obtained PhD in Japan, in Tokyo Autonomous Women University. And so far, I worked in the 2 large detector sites. So just shown by Professor Schutz, you saw there are several detectors in the world. I worked in this Louisiana. In Louisiana, I worked for LIGO detector. There are 2 LIGO detectors, and I worked in the Louisiana one. And then from 2015 to last year, I worked in Japan. There is another detector called Kagura, and I worked for the detector Kagura. Yeah, so now I'm at Cardiff University. So I'm the experimentalist working for the detector to develop the detector. And I'll show you a bit more about this in the next page. Yeah, so we want to do the astronomy detecting gravitational signals coming from the universe. And the detectors are L-shaped like this, and each L line is 4 kilometer or 3 kilometer. So it's a very, very, very large machine to detect very small signals of gravitational waves. So this large machine, large machines have very different parts, and it's very, very complicated. So the pictures are just an examples. So we have a lot of mechanics. If you look at the left bottom picture, you see some metal frames. They are something to support our optics. The optics part is the core part to detect gravitational waves. So we have used this very big optics. This is a fused silica mirror. And we use very huge mechanical stage. It's also part of the machine. And we use a lot of electronics and a huge computer system. And our job at the detector site is to put everything together. We connect everything, or we assemble machines to make one detector. So our job at the sites is to make the detector work stably. And also we must make the detector sensitivity very good so that we can observe gravitational waves from even further from the universe. Okay, can you go to the next page? Yeah. Okay, so this is another detector. The pictures in the previous page is LIGO detector in Louisiana. This is a pictures from Kagura detector. So Kagura detector is built underground. So if you look at the picture on the left, it's this 3 kilometer L part is in this very long tunnel underground. We also have the control room, and we have complicated parts. So our job is the same. We put everything together and make it work. Yeah, so this is my research topics. Yeah, thank you. This is my introduction.
Thank you, Keiko. So that's a little bit about detectors on the larger scale at these detector sites. We're moving on now to our third panelist, which is Dr. Aldo Ejlli. So Aldo, do you want to turn on your video and unmute and tell us a little bit about yourself and what you work on?
Okay. Hi, Chris. Hi, everyone. Thank you. Nice to meet you virtually. So I graduated in Ferrara with my bachelor and master degrees, and I did my PhD doctorate in Ferrara, still in Italy. I did 1 year there, and then I joined Cardiff in 2018 as a postdoc research associate. So if you can move to the next slide to explain a little bit my work. As I said, I'm an experimentalist. I start my adventure in an experiment called PV loss at Ferrara, which want to measure the vacuum magnetic birefringence. What is vacuum magnetic birefringence? So imagine now a place where, let's say, a part of a space where you remove the gas, and what this left one is nothing, so vacuum. This is the definition of vacuum. But can you go back one slide? Yeah, this is the definition of vacuum, and but in reality, what is left there is a virtual process of virtual particles that creates an annihilate that is called the quantum vacuum, or the quantum electrodynamics explained very well with this process. So what we did is to paralyze the vacuum with these two blue cylinders with a magnetic field and send light to see if they exist. This is a direct measurement. What we to amplify the effect, we send the light and we bounce it back and forth 450,000 times. Is equivalent to have a magnetic field from Cardiff to Berlin, for example. And we went very close to measure the effect, a factor 7. But what we conclude then, we need an upgrade of this experiment with bigger magnetic fields, bigger magnets, higher magnetic fields, and we are planning in the future to have this. Then I moved on 2018 and joined LIGO Scientific Collaboration, and I joined here the group in Cardiff that want to build something for the future detectors. And as you can see, these LIGO detectors are very big, 4-kilometer arms, and what they do is to see if there is a change in the orthogonal arms of the length. If there is a change and you have some photons coming out from that beam splitter, this is the dashed line, and these photons, which is the discrete nature of the light, goes directly to the photodetector. So the photodetector then has a noise, intrinsic noise to the photons, because these photons are going to the photodetector is similar to the noise of the drops of rain in your umbrella. So they make a noise. And what we want then, that all the other noise to be lower. So also the power supply and the electronic components of the photodetector make noise. Exactly when you open, let's say, for similarity, taps of the water, you hear that noise. So the electron flowing in the electronics of the photodetector make noise, and what we want to build for the future generation of for the upgrade of these big detectors is a ultra low noise readout. So we are building here in Cardiff, which is this picture on the right-hand side, this ultra low noise electronics for upgrade LIGO. So next slide, please. Last but not least, we are building a new experiment here in Cardiff that search for signatures of quantum space-time. So this is a tabletop experiment. We want to build two co-located Michelson interferometers, and they will look for signature of quantum spacetime. What is the quantum spacetime? Exactly as photons are quantum, we think also spacetime is quantized at the level of the Planck scale. So at this level of the Planck scale, in the interferometer, we want to see if the light gets affected by this quantization of space-time and will come out at the port of the detector as a noise. But correlating the two noises, we will be able to see if there is a signature of the quantum space-time, not only for quantum space-time, but will be sensitive also to high-frequency gravitational waves and dark matter candidates. So thank you, Chris. This is my...
Thank you very much. So that's other things we can do with detectors at the end there for beyond detecting gravitational waves, detecting dark matter candidates, and so on. An awful lot of other stuff we can try and do. Okay, we'll move on to panelist number 4, and we're on to Dr. Hong Ki. So Hong, do you want to tell us a little bit about yourself and your work?
Yes, thanks, Chris. Hi, everyone. I'm so glad you're here. I'm going to briefly talk about myself and my work. I studied spacecraft design and engineering from Beijing University of Aeronautics and Astronautics as an undergraduate student. Then I went to the National Astronomical Observatories of China in Beijing to do my PhD degree. But I dropped out the program and took a master in 2011 because one day Professor Bernard Schutz went to our institute and gave a talk on gravitational waves with LISA space detector. And I was very intrigued, and I said, this is exactly what I wanted to do. Because it requires math, and I enjoyed math, and I thought my undergraduate major in space engineering could be useful as well. So luckily I got an offer from, I then went to the United States to do my PhD in the University of Wisconsin-Milwaukee and majoring in physics. And after graduation, I spent a summer vacation and then came to Cardiff to work as a research associate. And I have been a member of the LIGO Scientific Collaboration since 2015 and a member of LISA Consortium since 2019. And I list a few things about my work. So in 2015, together with my collaborators, I searched for the first gravitational waves from data in advanced LIGO's first observing run. And in 2017, together with my colleagues, I measured the Hubble constant with gravitational wave standard sirens using Professor Bernard Schutz's 1986 method. He just mentioned that it's a very, very brilliant idea. And in 2019, I developed, together with my colleague, I developed fast and accurate gravitational wave inference algorithms and code so that we can extract gravitational wave source properties such as the masses, the distances faster and accurately. And last year, together with my collaborators, I measured the galactic center black hole spin. Chris, would you move to the next slide, please? So my work focuses on data analysis and astrophysics, but today I'm gonna focus on mainly the data analysis and how to identify gravitational waves and extracting their source properties. And the gravitational waves that can be detected by advanced LIGO and other detectors are mostly 0.1 to 100 second transients, and they are very faint, both making the detections very challenging. And what we can do, so as we said, LIGO is big science. It requires a lot of collaborations, and Keiko and Aldo works on the detectors and the experiments, and other colleagues, together with other colleagues. And after they have the data, they pass the data to the data quality team. And there is a team, this team will work on cleaning and calibrating the data. after they make the data, like get rid of the things, the glitches, the noise, get rid of the unwanted, like the things, then they pass the data to us. And after we get the data, we want to find gravitational waves in them. How are we gonna do that? The data we have in LIGO is basically time series. So it records how much fluctuations in the detectors as a function of time. So at each time there's fluctuation and it's recorded. So we can plot that out, and we can do several things to search for gravitational waves. One thing we can do is to preliminarily search for gravitational waves in the data. Well, if we plot a time frequency figure, there's a terminology called spectrogram. If you read articles about that, now you know it's essentially just time frequency theory. And these plots can separate gravitational wave transient event from noise. I'm gonna show you a video, about 30 seconds, and I want you to pay attention to two things. One is what you can hear that changes. The second is what you can see that changes. Can you hear anything different? Can you spot anything different? Chris, I cannot hear the sound here. Would you mind me? I mute and you play it.
Yeah, I'll share it. I'll share it this time with the audio. Apologies. There we go.
So the x-axis is time, the y. Toward end, there is a whoop sound. I hope you hear it. And also we saw that there are two lines there, not two lines, three lines there. Each line is in each detector. I couldn't change it. And that's would you stop at some point? Yeah. So there were three detectors. The top one is LIGO Hanford, then LIGO Livingston, then Virgo. And in each detector, you can see a line that goes from bottom left to top right. And that is a gravitational wave signal. That is an orbit signal. But for most of the gravitational waves, we cannot see it that way. And in practice, it's difficult to see it that way because they are buried in noise and difficult to spot. And in practice, we use a technique called matched featuring to find signals in our data. What we do first is we produce a lot of gravitational wave signal templates calculated from general relativity. And these will be like the wiggles, like how they are going to wiggle with respect to time, how the gravitational waves will wiggle with respect to time. And then we compare these millions of wiggles with the data we observed and see which wiggle best match with our data. And then that is going to be the gravitational wave. And if there is nothing matching, then there's no gravitational waves. And from there, if we can find a match, then we will be able to identify gravitational waves and also extract their source properties, such as how far away those sources were, those gravitational waves initially were, the two black holes were, and what masses of the two black holes and what the final mass after the two black hole collide into one. So Chris, would you show us this video around 2 minutes? So this
has shrunk by 5 millimeters. The effect of a gravitational wave is so minuscule and easily confused with random noise, you need a smart data analysis technique. Scientists hope to identify the patterns of gravitational waves by comparing the wiggles they measure in the experiment to the wiggles they expect from the gravitational waves. That's like trying to identify a song being hummed at a noisy party. A very, very noisy party. Imagine your whole life you had been deaf until one day your hearing was restored. You'd be able to explore the universe in this whole new way. That's why detecting gravitational waves is so significant. It's a completely new way of studying the universe. Anytime there's a new way to investigate the universe, we discover things we didn't expect.
Yeah. So after we extracted the source properties, like the masses, the distances, the sky locations of these gravitational waves, we can do some really cool science. And my colleague Fabio will talk about gravitational wave science games. Thanks.
Thank you very much, Hong. So next up, we've got our fifth and final panel member, so Dr. Fabio Antonini. Fabio, you want to unmute and share your video, and you can tell us a little bit about you and the work you do with all this data that Hong's just described.
Okay, thank you very much, Chris. Thanks for organizing this beautiful event, and I'm very happy to see how many people actually joined. So I will try to be short so we can have plenty of time for discussions and questions. Well, I spent the first 9 years of my career in the US, Chicago, and Toronto before joining, before coming to the UK approximately about 3 years ago, actually. And I am a lecturer here in Cardiff, and I actually joined Cardiff November of last year. So my research interest is the astrophysics of gravitational wave sources. So what I do is to try to understand what gravitational wave sources, the detection of these sources, tell us about astrophysics, about the evolution of stars and how they evolve in the universe. And one of the main questions that I try to address, this is mostly theoretical work and numerical, is how you can form merging black holes. So how you can form a pair of black holes that are so close to each other that they can merge actually through the emission of gravitational wave radiation within the age of the universe, starting from two stars. How two stars that evolve together can produce black holes. This is a question that we don't know the answer to, and we're trying at the moment to answer, doing numerical simulations and analytical work. So the black holes that have been detected by LIGO are the product of the evolution of massive stars. So these are stars that have a mass much larger than the mass of the sun, from 10 to 50 or even 100 solar masses. So they're very massive stars. And they produce black holes with masses in the range between 10 to 50 times the mass of the sun. And so if you can go to the next slide. So these are relatively small black holes if you compare them to another type of black hole, which is called a supermassive black hole. So these black holes are much more massive than black holes that have been detected by LIGO. Their masses go between a million solar masses, so a million times the mass of the sun, to billions of times the mass of the sun. And they they are found observationally at the center of galaxies. And the most clear example of, and the strongest evidence, I would say, for the existence of this supermassive black hole is the supermassive black hole that we find at the center of our own galaxy, the Milky Way. In fact, people that have studied the orbits of stars around the center of our galaxies, that are depicted in this figure in the background, have studied the orbits, so how the stars go around the galactic center, and they have shown that there must be a compact object residing just at the center of the galaxy that has a mass of about 4 millions the mass of the sun, 4 million times the mass of the sun. So a very massive compact object compared to the black holes that, again, have been detected so far by LIGO, or that can be detected by LIGO. And on the right, you see a cartoon picture of the of LISA, the laser interferometer space antenna, which I would say it's kind of an extreme version of LIGO. It's the length of the arms of the interferometer in this case are going to be around 3 million kilometers. Okay, and because of this, LISA will have to be in space, and we fly, I hope, by 2035, but we're not really sure when this will happen. But it's a future experiment, so it's a laser interferometer. We will have lasers in space that will detect supermassive black holes merging with each other, and potentially also supermassive black holes merging with smaller black holes similar to those detected by LIGO, with so the merger of these smaller black holes with supermassive black holes. Okay, that's my part. I hope we're going to get lots of questions.
Yeah, we've certainly got lots coming in. Thank you very much, Fabio, and all the panelists there. We'll move on to questions for the last part of the session. In fact, I will stop sharing, and I think what we can do, I think, is turn on videos of all the panelists. So you should, in theory, be able to see them all on screen. And we've got some coming in, so I will pick one to start with. I'm going to go back to Bernard. I think there's a question coming from someone that says, if Einstein discovered that gravity isn't a force, then why is it considered to be one of the 4 fundamental forces? Still.
Yeah, we actually, the word force is a problematic one, and so often we talk about interactions, the 4 fundamental interactions. Gravity doesn't exert a force in the normal sense of the word, because if you're in free fall and you're affected by gravity, you still feel weightless. You don't experience the kind of acceleration forces that you get if you get pushed by a person or something like that. So, but we do have an interaction with gravity, and the interaction is most clearly shown in our detectors. Our gravitational wave passes through our detectors, and it changes the distances between the mirrors at the ends of the arms in our detectors, and so that's a real physical interaction. And so you can leave the word force aside. It's one of the 4 fundamental interactions.
Excellent. Thanks for some fundamental physics in there. Thank you very much. Right, the next question, I think we'll go back to probably to Hong, actually. So question has come in saying, I'm guessing from a teacher, given the question, it says students ask why gravitational waves scale with distance to source, not the inverse square of the distance to source. So we're used to light getting, if you move it twice as far away, it gets 4 times fainter. That doesn't happen with gravitational waves. Could you explain why we talk about gravitational wave scaling just with distance, not distance squared. So that's one for.
Are you sorry? Who's this question to?
Honga, I thought could do that one.
Hi, Chris. Sorry, would you repeat the question again?
Sure. So why do gravitational waves scale with distance rather than with distance squared away from the source?
So we are talking about the fluctuation of the gravitational wave, not the intensity of the gravitational wave. Usually when we talk about the intensity, like the light, how much light, the light power, and it will decrease as a function of distance squared, but the fluctuation itself is not intensity. It will have to be intensity if you square the fluctuation. So the fluctuation itself is proportional, like it's decreasing by 1/d. Yeah.
Thank you. So it's all because we're mentioning that measuring that amplitude of the disturbance rather than the intensity of the disturbance. Excellent. Thank you. Okay. The next question I think we'll take to probably Aldo. It refers to something that you mentioned. You were talking about a different experiment and by bouncing things backwards and forwards. But if you can bounce light between mirrors 450 times to form a path from Cardiff to Berlin, what's the advantage of building a tunnel over 4 kilometers long to bounce light the same distance? So why are these detectors so big, I guess, is the question.
Yeah, no, they are so big for one reason, because the gravitational wave has a very long wavelength, okay? And what you need, actually, you need maybe 380 kilometers of arm length to see all the change of the gravitational waves arm. So what you do is just to build some Fabry-Perot cavities, or better, bounce the light back and forth in order to be sensitive to the gravitational wave, let's say the length of a gravitational wave, to be exactly sensitive to that precise wavelength. If you bounce the light too many times back and forth, then you lost coherence between movement of the mirror and the gravitational wave. So you lost coherence and you cancel a signal. So you need a precise number of bounces for a long wavelength of gravitational waves.
Excellent, thank you. So it's that careful balance, as you say, between the number of times.
Yes, absolutely. There is a careful balance, and if you can see this have the frequency of 100 hertz. You know, the speed of the light is 3 times 10 to the 8. You calculate what is the wavelength, and you end up to have some kilometers wavelength, more bigger than 4 kilometers. And what you do is just to put some bouncing of the light back and forth in order to cover that kilometer wavelength. If you do more bouncing, then you have a decoherence between the gravitational wave that moves the mirror and the light that amplifies back and forth. So you risk to cancel the signal. And the LIGO detectors and the Virgo detectors are tuned to have a sensitivity in frequency between 40 to 7 kilohertz, 40 hertz to 7 kilohertz. For a higher frequency, then you need the smaller detectors, and for lower frequency, you need bigger detectors.
Excellent, thank you very much. We're going to stay with detectors, and I'm going to come to Keiko now. So the answer to this question is potentially very long and complicated. So I'm sure I know there's an awful lot of detail goes into this, but it's about how are gravitational wave detectors and the instruments tested and calibrated to make them so sensitive? Presumably, it's not possible to generate a test gravitational wave. You know, we can't take 2 black holes next door and smash them together to test these things. So how do we test these gravitational wave detectors, given they're so sensitive?
Yeah, it's a difficult question. So first of all, we want to mention what we are measuring by the detectors. So when gravitational waves come to us, the space-time is squeezed or stretched. So the lengths between 2 objects change. So the two objects for us in the detector are interferometer mirrors, and we are measuring the distances between mirrors by our instruments. So we can mimic the fake gravitational wave by moving the mirror. We cannot use black holes to make the distance change, but we can just simply push the mirrors with instruments, and we can mimic the gravitational waveform. So that's how we test the detector. And of course, we must know how much meters we are moving. So that's the calibration part.
Excellent. Thank you. Thank you very much. I'll come to Fabio. Fabio now. So this is one that you can probably address. So there's probably a very short answer and also a longer answer to this one. Do gravitational waves have any practical effect on space on a large scale, such as compressing gas clouds or pushing around massive objects out in space?
Well, the short answer is no. Space-time is very stiff, so it's hard to perturb it. It's very difficult to perturb it significantly enough that you would cause any damage to large-scale structures in the universe or even stars. So as we mentioned before, these waves cause very, very small perturbations, and that's why they are so difficult to detect, and that's why it took such a big effort and such a long time in order to detect them.
Okay, thank you. Right, so we're coming towards the end. We've got a few minutes left. So I know there's a bunch of questions that panelists have very kindly been answering in text, so you should be able to see those, and we'll try and put a log online somewhere and circulate the answers to those that have been typed, as well as the answers we've got to in this session as well. Actually, I'm not sure who wants to take this. Actually, I can see that Hong has just started typing an answer to this one, so I'll ask you verbally because I think it's quite a fun one. So another question that comes from students. How near would we need to be to a black hole merger or neutron star merger to be able to feel the effects of the gravitational waves rippling through space?
Is this a question for me?
That's for you, Hong. Yeah, if you want to take that one.
Okay. So how far or how near, it depends on how heavy the gravitational wave is. So the heaviest gravitational waves that can be detected by LIGO depends on the LIGO's sensitivity. We know that heavier black holes corresponds to lower frequencies. And LIGO can work at frequency as low as 10-20 hertz, and that would correspond to a gravitational wave of about that made up of masses about a couple of hundreds or a few hundreds the weight of our sun. So if that's the case, then we have that heavy binary system, like back to black holes, then we can put that heavy black holes farther away for us to be able to detect it, because it's louder than if the black holes are lighter. And if the black holes are lighter, then we will have to pull them closer to us to be able to distinguish. It's like in a room when people are talking, and that person talk very loudly, then you'd be able to hear it from farther away. But if they talk quietly, then you have to go closer. And how near? I think there is no limit to how near. You can get close to like zero distance as as long as there is a gravitational wave there. But how far away? So far for LIGO, we have detected gravitational waves as far as 5 gigaparsecs, which is about 16 billion light years away. That is a distance that takes light 16 billion years. Recall that the solar system formed 4.5 billion years ago, and our Milky Way galaxy formed 14 billion years away. And these gravitational waves they formed even before our galaxy or our solar system were formed, and they just propagate toward us while we are evolving. So I hope that answers your question.
Thank you. There's another actually way of interpreting the question as well, which I was talking about with the first detection of gravitational waves in 2015, which is whether we as people could feel these gravitational waves.
Wow.
If a ripple comes through space, I did some back of the envelope calculations back then, and I think if we were as close to these black hole systems as the Earth is to the Sun, the pressure with the density waves, the change in gravity would stretch our inner ear enough that we would hear it at a sort of the sound of chatter in an office. If we were the distance of the moon, I think, from the Earth, then it would be painful to hear, or we'd definitely be able to hear it, I think. And that if we were 3,000 kilometers away, it would be painful to hear from these. But at that point, you're 3,000 kilometers from 100 solar masses of black hole, and you have bigger problems than your ears hurting, because you'll be spaghettified, or be getting spaghettified by the sheer tidal forces. So that's a different side to the question. Aldo, you have a hand up? Just
yes. I want just to say that usually these gravitational waves has a strain peak of 10 to the minus 20, 22. So you can calculate, we have 2 meters, okay? If you want to see ourselves squeezing an order of centimeters, then you calculate that this amplitude scales with L. So you can go as close to the gravitational wave source in order to see like 1 centimeter of stretch or 10 centimeters of stretch. So you can in principle, by knowing the strain of these big black holes that emerge together, and how close they can go, how close we can go to see that 1 centimeter or 10 centimeter, you can calculate it very easily. Just straightforward calculation.
And it's very close because these gravitational waves are so weak, right?
Yeah, it is very close. So you need, we have 2 meters, then the strain is 10 to the minus 22. You need 20 orders of magnitude, in meters.
Okay, thank you for that. We're past 5 o'clock, so we said this would be an hour long. So we're at the time limit. So I appreciate people will have to disappear for other things. So Grace has put in the chat a message saying thank you for joining us, and that the whole team behind the Cardiff Science Festival would be grateful you could fill in an evaluation form. So if you could click the link there, it would be great to see some evaluation of what you've enjoyed about the session, whether you want to hear anything else. I think everyone booked on Eventbrite, so we will be able to circulate some information about that. We'll try and compile the answers to the questions that we've either answered verbally or that have been answered by panelists answering them in text, which means we've got through quite a lot more there, I can see, as we go along. So hopefully those will be recorded somewhere. So apologies to those who we didn't get to the questions that you asked. I can see a couple are being answered in text, and so we may get to those after the event. But we should stop there because it's 5 o'clock, and we fortunately have come to the end of our time slot. So thank you very much to the panelists. So Bernard, Hong, Aldo, Keiko, and Fabio. And thank you to Grace for stage managing from behind the curtain and making sure everything went seamlessly. I hope this has been interesting for everyone who attended the session, and that you continue to look out for gravitational wave news. There are obviously lots more events as part of Cardiff Science Festival, so if you do have any more you want to attend, then cardiffsciencefestival.co.uk. Everything's online, so even if you're based in India or Pittsburgh or Slovakia or Cardiff, then or anywhere else, you can go and attend any of these events. So do go and have a look. It runs for the rest of the weekend. So thank you very much to everyone who came, and thank you to the panelists. Those were excellent questions and fabulous answers. Goodbye, everyone.